Step number 3. Now we have a recurrence and we want to compute the value of this optimal solution. And how? Now let's write a recursive function to calculate this recursive relationship. Okay, the input here is the dimension array and I and j. That means we want to solve the subproblem from AI, and AI has dimensions pi minus 1 and pi. So first we check if I equals j. If I equals j, we return the value of 0. Otherwise, we calculate the value for mij by looking at all possible candidates for k. And then for each value of k, we need to calculate mik and mk plus 1j, and we do so by these two recursive calls. Okay? And also we calculate the cost of the final multiplication, and then we check if this cost is smaller than the current minimum cost. If it is, we update the current minimum cost. Okay, and then we return this value mij. This is a direct implementation of this recursive relationship. However, this algorithm is very expensive. Let's write down the recurrence of running time. So Tn equals, let's just count how many subproblems we try to solve here. So for each k, we called two subproblems. So T, the first one, had the size k, and the other one had the size n minus k, right? And we do this for k goes from 1 to n minus 1. Okay? So we can see we have solved a large number of subproblems, right? So this is the call graph of the execution of 4 matrices. And you can see there are already many subproblems generated. It turns out the running time of this algorithm is still exponential in n. Okay? Because if you solve this recurrence, and you can end up with a complexity of 2 to the power of n minus 1. It's still exponential. Well, it is better than the brute force, remember. The brute force method has a constant number as the complexity, and that is 4 to the power of n. So it is better than the brute force algorithm, but it's still too expensive. Okay? But then we realize, okay, why this happens? Is it because we have so many different subproblems, or is that because we repeatedly calculate the same subproblems time and time again, right? So if you look at the call graph carefully, you actually can see the subproblems in green are overlapping subproblems. Okay? So it's another important property of problem that can be solved using dynamic programming approach. It is called overlapping subproblem property. So we have relatively few distinct subproblems. Okay, in this particular problem, because we try to solve for mij, I goes from 1 to n, and j goes from 1 to n as well. So the number of distinct subproblems is actually n squared, right? So we have relatively few distinct subproblems. But this recursive algorithm may encounter each subproblem many times. Okay, so we have two solutions to solve this problem. We can store the outputs of distinct subproblems during the execution of the recursive function, or we can have a bottom-up algorithm So we compute the optimal cost by using a tabular bottom-up approach. And this bottom-up approach usually is more efficient than the top-down recursive approaches. How to design a bottom-up algorithm to calculate MIJ, right? So let's draw a table for MIJ. This is a table for MIJ. The result we are looking for is actually in M1n. Okay, so here is M1n. This is the final answer we are looking for. And let's look at this recurrence carefully. For I equals j, that's the diagonal. We know the value is 0. So 0, 0, and 0. Okay. If the length of the matrix chain from AI to AJ is L, so L equals j minus I plus 1. If this is the length of the matrix chain from AI to AJ, then this calculation going to use the optimal value of the subchains. And these subchains of the matrix chain from AI to AJ, they all have the length smaller than L because they are subchains, right? So this gives us a hint. So we calculate these solutions for subchains of length 1, and then from there we calculate the solutions to subchains of length 2, and so on, until we reach to this corner. And here we have the chain of length n. Okay, so let's do this. So we initialize the diagonal of this table with 0. And then we have this for loop. L goes from 2 to n, and L is the length of subchains. And we calculate for all subchains with length L. So I goes 1 to n minus L plus 1, and we calculate the ending index of this subchain. The subchain from AI to AJ has a length of L. We initialize MIJ with a large number, and then we try all possible splits. K goes from I to j minus 1, and we use this recurrence to calculate what is the cost if the split happens at K. If this cost is smaller than the current best MIJ, we update MIJ with this new cost. Also maintain a table of S. It actually store the choice of K here. We need this information when we actually construct the optimal solution. Okay. In terms of complexity, the number of subproblems is n squared. So there are n squared number of entries in this table, and each of them we need to perform this for loop, and this for loop has a complexity of big O n. So overall, the total running time is n cubed. So remember, the brute force algorithm is exponential, and a naive recursive version is also exponential. And here, the bottom-up version is actually an n-cube algorithm. Okay. So let's look at an example. If you have 6 matrices, A1, A2, A3, A4, A5, and A6. Okay. So first of all, for the subchains of length 1, that's single matrix, we have the cost 0 over here, and we get this level. Okay, so these values corresponds to the cost of multiplying two matrices. And then from there, we have to use this recurrence, okay, to try different options and pick the minimum one. Like for example, if we look at this entry, and that is M25, that is the optimal solution for the subchain from A2 to A5. In order to calculate this, we have to try different possible locations for the splits. So K goes from 2 to 4, right? So when K equals 2, that means the split after matrix A2. And we have two subchains. One is just A2 itself, is here. The other is A3 to 5, okay, so it's here. So this is entry M35. You're going to use these two values plus the cost of the final multiplication. That's one option. And then you calculate the other two options in a similar way. After that, you compare these three values and you pick the best one. And you put the choice, the optimal choice, in the table of S. So here, the optimal choice is 3. That means the optimal split happens after matrix 3. So we have A2, A3, and then A4, A5. Okay? So this is an example of the calculation of Mij. Now, the last step is an optional step. For some applications, we do need to construct the actual optimal solution. Okay? For example, we can have a recursive function, and we use the values or information we stored in the table S to actually construct the parameterization of the optimal order. And I leave this as an exercise for you to see how this recursive function works.